In this video, we will generate the GAMMADIST probability density function and cumulative distribution function, and its Taylor Maclaurin series sum for both. Our value for alpha will be from 1 to 2, so data validation, list of items, and this will be from 1 to 2. We'll copy this and paste it here. So our alpha will be from 1 to 2. And our value for beta will be from 1 to 6. So data validation, list of items, will copy from 1 to 6. So our value for beta will be from 1 to 6. And value for k will be data validation, list of items, and this will be 0 or 1. 0 if it is probability density function, 1 if it is cumulative distribution function. So your values are 0 or 1. Next, we continue with the data set, which is equal to array formula. GAMMADIST of the x values, comma, this will be our alpha, and this will be our beta, and 0 because if it is probability density function. And likewise, the cumulative distribution function is array formula, GAMMADIST of the x values, and this will be our alpha, followed by our beta, and it is 1 because this is the cumulative distribution function. We're not using k because this belongs to the series sum expansion. And our k series sum is x to the power alpha minus 1 plus k times the summation of x to the power n, where a equals the coefficient and n is from 0 to infinity. Can start from 0 up to infinity. In this case, 16 is good enough. And the coefficient, so r, the formula, minus 1 raised to the power n, divided by, now the denominator has 3 parts. The first part, beta raised to the power n, raised to the power n. The second part, times factorial n. And finally, the third part, times the quantity alpha plus n raised to the power k. So the quantity alpha plus n raised to the power k. And we'll close this. And now we can continue with the Taylor Maclaurin series sum expansion, which is equal to array formula. The numerator, that's x raised to the power, the quantity alpha minus 1 plus k. That's the first part. Now the second part. It's the summation. So series sum of the x values. That's x values raised to the power n, where n starts from 0. This is our n. Starts from 0, incremented by 1. And the coefficient a, there's the coefficient a, which is this range. That's our serious sum. Now that's the numerator, now the denominator. The denominator has two parts. The first part, gamma of alpha, the gamma of alpha. The second part, beta raised to the power alpha. So times beta raised to the power alpha. And we close this. Then enter. And we chart. So right now at k equals 0, these values are the same. Meaning this expansion approximates the probability density function. At k equals 1, our expansion approximates the cumulative distribution function. Let's chart this. Insert chart, and we will use scatter chart. And show the series, the trend line, polynomial to the 6th degree. And the label, use the equation. And for the legend, we'll put it on the left. That's for the legend. And let's go back to the series. The point size will be the largest. And the color of the GAMMADIST, there's no yellow, so we'll use the green. That's green. And go back to the series, this one, since it's the expansion which approximates both, will have no point size, but the line thickness will be maximum. And here's our trend line and polynomial to the 6th degree. We'll clean this vertical axis. We want the number format to be none because there's so many decimals here. So the vertical axis, the number format, none. That's better. So here's our trend line and polynomial to the 6th degree. Next, we'll calculate this polynomial regression coefficient using LINEST. To do that, we complete the 1, x matrix, starting with the power. This is the LINEST matrix or 1, x matrix. We'll start with the power, which is transpose 0 to 6. And the elements of the LINEST matrix. So array formula of the x values raised to the power 0 to 6. Then enter. And we calculate LINEST, starting with the probability density function, LINEST, data y, and data x. And enter. Then the LINEST for the zero-sum expansion, data x. And finally, the cumulative distribution function, data y and data x. then enter. So here, let's compare. If you allow k equals 0, so the expansion approximates the probability density function, and their polynomial regression coefficients are the same. Here, that's the polynomial regression, they're the same. If you say k equals 1, the expansion approximates the cumulative distribution function, and the polynomial regression coefficients are the same. We go to 2 right now because this is 1, so we can increase that to alpha. Increase our alpha to 1, and you can toggle this. So there is an error because this is only, our expansion is limited only to n equals 16. We can go higher and this will be eliminated. 1.5 and 1.6, 1.75, and we can toggle it to 1 and 2. Suppose I will use beta equals 2, go higher. So at alpha 1, this is our alpha, it's 1. That's because this is an expandist. But if you go higher, alpha equals 1.25, it's no longer expandist. You can toggle between k and now it's the probability density function. That's a probability density function. And if it is k equals 1, cumulative distribution function. Let's increase our alpha to 1.5. And we toggle back to the probability density function and the cumulative distribution function. And if we go to beta equals 3, we can go back to 1, which is expandist or exponential. Then we go higher, 1.25. We can toggle back to 0, which is the probability density function, and, or the cumulative distribution function. Goes to 1.5. So this completes the use of GAMMADIST in cumulative probability density function, cumulative distribution function, and the Taylor-Maclaurin series sum expansion and Linus polynomial regression to generate the trend lines and datasets of the GAMMADIST both in cumulative and probability density function.